Hello and welcome back, everyone. Our goal today is to talk about computing modular inverses. So what's the setup for our modular inverses? Well, we have to have something to work modulo, so I'm going to call that n. So this is what we call the modulus. So everything in this video we're going to work modulo something called n, unless I say otherwise. And then we have some a here, which is going to be an element of the integers, but we're thinking of it really modulo n. So remember, there's only n things mod n, but there's infinitely many integers. And that's because sort of when I think about an integer mod n, I'm really sort of thinking about it as all the integers that have the same remainder when you divide it by n. So when I think of, say, 7 mod 5, that's the same thing as 2 mod 5, and so on and so forth. But I'm just going to think of this thing as living in the plain old integers just for purposes of this. And so then, when I talk about computing modular inverses, what do I mean? Well, we're going to call something b the inverse of a mod n if a and b multiply together to be 1 mod n. Or if you want this is purely symmetric, a and b are inverses of each other if a times b is 1 mod n. That's a different way that you could think of the same thing. So, just as an example, 3 inverse mod 20 is 7, because 3 times 7 is 21, which is 1 mod 20. Now, we do have to be careful because inverses don't always exist. But fortunately, we have a big theorem that tells us when inverses actually exist. Namely, what that theorem says is that an integer a has an inverse mod n if and only if a and n have GCD 1, or if you prefer, are relatively prime. Because remember, we just said relatively prime means they have no factors in common, or their GCD is 1, whichever way you want to think about it. So I was thinking mod 20 just a second ago for this example. 3, it had an inverse mod 20, but if I took something like 15 won't have an inverse mod 20 at all. And that's because the GCD of 15 and 20 is 5, and 5 is not the same as 1. So in today's video, my goal is to go over how to use the extended Euclidean algorithm to calculate inverses when they exist. But before I do that, I want to do a slightly longer example of sort of doing this by hand just to make sure we're comfortable with it. So we're going to work mod 14 for this example. And mod 14, there are 14 things, which I have written here for you. Or if you want to be super technical, I've written representatives of the 14 things for you. Because remember, of course, there is a 15 mod 14. It just is the same thing as 1 mod 14. So the first thing I'm going to do is cross out everything that's not going to have an inverse. So 0 will never have an inverse, except maybe mod 1. But there's only one thing mod 1, so you probably just shouldn't think about mod 1 basically ever. 1 will have an inverse. 2 won't, because again, 2 and 14 share the factor of 2. 3 will, 4 won't. In fact, actually, since 2 is a factor of 14, all the even numbers are not going to have GCD 1 with 14. So in fact, you can go ahead and cross out all of those. And then there's one more thing that's not going to have an inverse. Namely, that's going to be 7. Because again, 7 is a factor of 14, so 7 shares that factor with 14. So at the end of the day, when we write this down, there are a total of 6 elements, mod 14, that have an inverse. I will go ahead and note for later, we give a name to the number of things, mod a number, that have an inverse. We're not going to emphasize this yet, but just so that you've seen it before when I talk about it, this thing we're going to denote by phi, and this is called the Euler Phi Function. And so phi of 14, we have just shown is 6, okay, because there are 6 things that are going to have an inverse. Now, the theorem guarantees me exactly these 6 things have an inverse, but let's go ahead and write down what that inverse is. So for 1, when I'm looking for 1's inverse, I'm thinking, what can I multiply 1 by to get 1? This is not a trick question. The thing I multiply 1 by to get 1 is 1. In other words, 1 is its own inverse, and that's perfectly allowed to happen. Things can be their own inverse. In fact, actually, there's something else that's always going to be its own inverse. Namely, if I scroll all the way down to the other side and look at this 13, 13 is minus 1 mod 14. And so if you think about it, minus 1 times minus 1, that should be 1, right? And so actually, you might guess, and it turns out to be true, 13 is also its own inverse mod 14. Now, if you don't believe me and you want to do this by longhand, you can write 13 times 13. That's 169. And if I think about that mod 14, well, let me just say, I definitely know 140 is a multiple of 14, so I'm going to throw that away. So if I throw away 140, that'll leave me with 29. But now I can throw away two 14s, which would give me 28. So that gives me 1. So the inverse of 13 is also 13. Okay, well that was the two easy ones. What's the inverse of 3 going to be? Well, I'm looking for something I can multiply 3 by in order to get something that is 1 more than a multiple of 14. In this case, the thing I'm looking for is actually 5, because 3 times 5 is 15, which is 1 mod 14. So that 5 is my inverse. Now, being an inverse is symmetric, because if A times B is 1, B times A is 1. So that means once I know the inverse of 3 is 5, I also know the inverse of 5 is 3. So now I want to know what 9 inverse is. So I'm looking for a multiple of 9 that is 1 more than a multiple of 14. Now, if you actually look carefully here, you might be able to guess that because 9 has to have an inverse, and it has to be one of these 6 circled red numbers, and 9 can't be the inverse of any of these other things, that means the inverse of 9 really only has 2 options. Namely, either the inverse of 9 is 9, or the inverse of 9 is 11. So we really just have to decide which of those it is. So what is 9 times 9 mod 14? Here's a helpful hint when you're calculating 9 times 9 mod 14. You can, of course, say, okay, that's 81. Okay, so 14 times 5 would be 70. So this is 11 mod 14. That's one way you could do it, and that's perfectly fine. Or, here's the other way you could do this. You could also say, well, 9 is minus 5 mod 14. And so 9 times 9 is the same thing as minus 5 times minus 5, which is the same thing as 5 times 5, which is 25, which is 11 mod 14. And that involves doing multiplication and math in your head with smaller numbers. But whichever of those you like, the point is 9 times 9, not 1 mod 14. What about 9 times 11? Well, what is 9 times 11 mod 14? Again, I can think about that as, okay, what's 99 mod 14? And then I get to think through my multiples of 14. And guess what? I don't know my multiples of 14 very well. Or I can use the same mental trick, which is that 9 is minus 5 mod 14. And 11 is minus 3 mod 14. So 9 times 11 is minus 5 times minus 3, which is 5 times 3, which is 15, and so it's 1 mod 14. And so what that shows is that, as we might have guessed, the inverse of 9 mod 14 is 11, and the inverse of 11 mod 14 is 9. Now, what you'll see here is there's always this kind of buddy system when I look at modular inverses. So in this case, 3 and 5 are buddies because they're each other's inverses. 9 and 11 are buddies because they're each other's inverses. And then we've got a couple things that are their own inverses. So 1 is always its own inverse. 13 is its own inverse. Every once in a while, there'll be other things that are also their own inverse, depending on what modulus you're working with. Now, I should remind you, before I jump into how we're actually going to compute these things, because I promise when we're working modulo giant moduli, we're not going to compute them by guessing and checking like we did just here. Before I do that, I want to remind you, if you take a prime modulus, then instead of having this weird sort of subset of things whose inverses you can take, it becomes very easy to satisfy this condition that the GCD with n is 1, because if n is prime, everything except 0 mod n has GCD 1 with it. That's basically what being prime means. And so when you go ahead and look at the structure modulo a prime, there will be no x's. Every single element will have an inverse, except for 0. Which is why, by the way, I picked 14, so that I would not have to write out a jajillion of these things. But it works just as well. So as a first example, let's look at something like calculating 112 inverse mod 1729. Now, before you get too far in this, you should probably check, does 112 actually have an inverse mod 1729? To figure that out, remember you calculate the GCD of 112 and 1729, and if you do that, you will find out that it is actually 7. So there is no inverse. So that was easy enough. Let's do one where there actually is an inverse. Let's calculate 115 inverse mod 1729. Now, I recommended the first thing you do is to calculate the GCD. Well, if you think about how we actually calculate the GCD, we do it with the extended Euclidean algorithm. So the thing I'm actually going to do is I'm going to run the extended Euclidean algorithm on the numbers 115 and 1729. So when we start the extended Euclidean algorithm, remember we write down, okay, here's our table, and so we'll start with our two favorite rows. 1, 0 will give me 1729. 0, 1 will give me 115. Now, it's not so hard to calculate that 115 goes into 1729 15 times. So, on the next line, I want to subtract 15 times 115 from 1729. So that means I'm going to still have a 1 in this column, but now a minus 15 in this column. And when you do this, you'll find out that you get 4. That is to say, when you calculate 1729 minus 15 times 115, you'll get 4. How many times does 4 go into 115? 4 goes into 115 28 times. So I want to subtract 28 times 4 from 115. When I do that, I know I'm going to get 3. And let's go ahead and make sure we do that from the rows. So I'm going to subtract 28 times this row from this row. So that will give me a minus 28 out front here. And now I have 1 plus 28 times 15. I definitely don't want to do that calculation in my head, but 1 plus 28 times 15 happens to work out to be 421. So now, fortunately, the harder part is done, because now we get to ask ourselves, how many times does 3 go into 4? Well, 3 goes into 4 one time. And so I need to subtract 3 from 4, which will give me 1. And I, in so doing, need to subtract this row from this row, which will give me a 29 here, and a minus 436 here. Now, if I kept going, we know what would happen. I'd ask, how many times does 1 go into 3? It would go in 3 times, and I would be left with 0. But remember, that means that 1 actually was the GCD. So by actually making this calculation, we have shown that in fact, if you believe our theorem, 115 does have an inverse mod 1729. And I claim that actually, if you look closely, we have found that inverse. Namely, what am I going to do? I'm going to look at this line. What does this line say? This line says that 29 times 1729 minus 436 times 115 is 1. Now, at first it might not be clear why I say this tells me what the inverse of 115 is, mod 1729. But what I want to do is I want to take this equation and I want to interpret it mod 1729. So mod 1729, this whole term is just 0. And so mod 1729, what this actually says is that minus 436 times 115 is equal to 1. And so that's exactly telling me that 115 inverse is minus 436. Now, you might prefer not to use minus numbers, and so instead of this, you might rather add 1729 to this, in which case what you'll get is 1293. So what I've just shown you is that if you want to know the inverse of a number modulo another number, you run the extended Euclidean algorithm on those two numbers. At the end, you'll either get that the GCD is 1, or the GCD isn't 1. If the GCD is not 1, well then there isn't an inverse. If the GCD is 1, then you look one square to the left of that GCD, and the number written in that square is the inverse. And the reason for that is because of what each row of this table means. Namely, this row means 29 times 1729 minus 436 times 115 is 1. And so if you look at that, again, mod 1729, the whole 1729x bit, it just disappears. And so the only thing you have left is, well, exactly your inverse. And again, if this number is negative, or if it happens to be a little bigger or a little smaller than your modulus, you can adjust the number by finding the residue mod that number. And so, our punchline for this video is that the extended Euclidean algorithm not only finds GCDs for us, the extended Euclidean algorithm also finds modular inverses. And the way you go about finding that modular inverse actually only involves knowing where to look in the table we already described how to make. So I think we couldn't really have hoped for anything much better than this. All right, I'll wrap up there for now. Next week, our plan is to talk about the complexity of algorithms, that is, how long it takes to do things. And one of the punchlines of next week is going to be that, in fact, the Euclidean algorithm is incredibly fast, even on ridiculously huge numbers. And so, because the extended Euclidean algorithm is all that you need in order to calculate modular inverses, that will tell us that, in fact, calculating modular inverses is also incredibly fast. But we'll talk about that more then. Have a great weekend.